Class, today's lesson is all about tangents, and when we're referring to tangents with circles, we're not referring to the opposite over adjacent side like we did in a right triangle. When we're talking about tangents for a circle, we're talking about a line that intersects the circle at exactly one place. And this line does have to be in the same plane, but that will be, all the ones we're going to do are going to be like that. So looking over here at circle C, you can see that line AB is tangent to circle C, and the point of tangent C is point A. Some of the questions are going to ask you about common tangents. Common tangents are tangent to more than one circle. And the ones you're going to do are going to be tangent to two circles at the same time. So looking at this example here, if I get a line segment, if I take that and connect it here, this line segment is tangent to both of those circles. It could be a ray or a whole line that goes across. That's not the only place though. I could have a common tangent there, and then for this one, because they have this point of tangency in the middle, I could have another line that kind of goes straight through like that, and because lines don't actually have like thickness, we would have just one point where all of those things came together. For these two circles, you can probably see that you can't draw a tangent line there because that would not work. This one here would only have one common tangent, and it would be like that. So depending on how the picture looks, there'll be different numbers of common tangents, and you can see more examples in your book like this if you want to see for other situations. I know this is the question you've all been thinking. How do you know if something is tangent? Because you can't just tell by looking at it, because things don't have to necessarily be drawn to scale. So here's how you're going to know. A line is tangent to a circle if and only if it is perpendicular to the radius drawn to the point of tangency. So this is the radius, point T would be our point of tangency. So because this is perpendicular, you would know that line L is tangent to circle S. So the questions are going to look a number of different ways for this. But most of the time you're going to be setting up the Pythagorean theorem and answering the question that way. So for this one it says determine whether GH is tangent to circle F. So again, I know it looks like it is, but we need to actually like justify our answer by showing that it's perpendicular. And here is a little trick. It's a little tricky sometimes to tell the way the book is referencing things, but it's saying that this segment is 8. This segment is 6, and if they were talking about the whole thing, they would have it drawn like this, and then say that the whole thing is 12. They don't have it drawn like that. So what they're referencing here is that just this portion is 12. So I need to figure out how long that entire part would be. I know that the radius is 6, and the radius is here also. So the whole way from H to F would be 18. So I'm going to check and see if this is a right triangle by checking to see does this work in the Pythagorean theorem. And you can go ahead and grab a calculator. So let's do 8 squared plus 6 squared to get 100. And you can probably tell, but where'd the calculator go? $100. And then you can figure out 18 squared is 324. And because those are not equal, this would not be tangent. So where it says determine whether it's tangent, you could just say it's not tangent. And to justify your answer, you could say it's not perpendicular to GF. For this one here, it says find the value of x, assume the segments that appear to be tangent are tangent. So they're letting you know that because this looks like it's tangent, it's going to be. So because BC is tangent to circle A at its point of tangency, that's going to make those perpendicular. So I can solve for x by using the Pythagorean theorem. So again, just go ahead and grab your calculator. I'll do it on mine here too. So we have 14 squared is 196, and 17 squared is 289. So I'm going to set this up. X squared plus 196 equals 289. I'm going to go ahead and then subtract that. 196, and then I can take the square root. So the answer would be the square root of 93. It doesn't say here what we need to do. If you want to just leave it the square root of 93, that's fine. Or if you want to approximate, that's going to be about 9.64 if you're rounding that to the nearest hundredth. Because the directions don't say, if you were to put 9.6 like on a test or a quiz, I wouldn't mark that wrong. For this next one's a little trickier. Because when you set up the Pythagorean theorem here, there's a little more algebra work you're going to have to do. The two legs are these two sides here. This first one is 4, but that doesn't specifically tell you that. However, that is a radius, and the radius here is x, so I'm going to go ahead and put that in there. What I'm going to do to solve this is I'm going to say that 4 squared plus x squared equals this entire thing, which is, I'm going to write x plus 2, but 2 plus x is the same. And I need to square all of that. So it's really important we channel our Algebra 1 skills. Maybe you put like a big star next to this one to reference back. But we're going to have to go through and remember how to square a binomial. Let's start out though with 4 squared, that's 16. Plus x squared, and please do not think you're just going to square x and square 2, because that's not the way that this works. Depending on who you had last year for algebra, the directions may have varied. What I liked my students to do is write it out twice, because that's what it means to square, to multiply it by itself twice. And then you can think either distributive property, or if you remember the FOIL method, where you multiply all of those parts together. So x times x is x squared. X times 2 is 2x. And then 2 times x is 2x. And 2 times 2 is 4. So when you have this, we have 16 plus x squared equals x squared plus 4x plus 4. So going through and solving, it ends up not being as hard as maybe it looks like. When you subtract x squared from each side, they end up canceling out. I have 16 equals 4x plus 4, and then we can solve that with no problem. So x is going to equal 3. In this theorem, it says if two segments from the same exterior point, so that point here is point B, are tangent to the circle, then they are, and you might be able to tell just by looking at these two segments here are going to be congruent. They're going to be the same length. I think of this as like an ice cream cone or maybe like a party hat. Either way, you have to kind of turn it around so you can see it. But those sides are going to be the same if they're both tangent to the circle. In this question, it says, find the value of x, assume that the segments that are tangent or appear to be tangent are tangent. So because r is on the outside of the circle and both of these are tangent, that's going to make them congruent to each other. So I can solve for x by just setting those equal. So x equals 6. Before I get to these last examples, I just want to point out some circumscribed polygons. If the polygon is going to circumscribe the circle, that means that each side will touch that circle at exactly one place, or that those sides are going to be tangent to the circle. So these are all examples where you have it, all of those segments are tangent to the circle. For these, you might have some that are tangent, but because all of them are not tangent, these would not be circumscribed. So when you do have these, you have to remember this property up here where you have the sides equal that are tangent. And when I'm looking at this one, it says the round cookies are marketed in a triangular package to pique the customer's interest. If triangle QRS is circumscribed about T, find the perimeter of this triangle. So the first time you maybe look at this, you might think, well, I don't have enough information because I don't have all of the parts of the sides. But if you can remember that each point is equidistant when we have these tangent lines, that's going to help you solve this. So both of these are going to be 10. For this one here, a misconception sometimes is they say, well, this part's 4 and this part's 4. But that's not necessarily true. And in this case, here's a point on the exterior, and both of those are the same. So both of these are the same length. So because this is 2 centimeters, this one's going to be 2 centimeters. And then because you know this whole thing is 8, you know that this part is 6. So both of those are going to be 6. Now we have enough information that we could find the whole perimeter. So depending on how you want to like chunk these things together, these 2 parts, that's 20. These 2 parts, that's 12. And then those 2 added up is 4. So when you add all those up, that's going to be 36. And the units are centimeters. And for this last one, it wants me to find x when they give me the whole perimeter. So what I would do is I would just write an equation and figure out everything I know, not including x. So here I have t, both of these parts are going to be the same. So since this one is x, this one's x. For u, a point on the exterior, both of those are going to be the same. This one is r, and both of these are going to be the same. And let me just grab a different color. And for point S, both of those are going to be the same. So what I have here for this perimeter is I have 1, 2, 3, 4x, and then add up all of those. So when I add up all of those, that's going to be 12. So 4x equals, when I subtract that over, that's going to be 6, or x equals 1.5. And there you go. We will practice this in class, and I hope Colby wasn't too much of an interruption.